Okay, so last lesson we looked at arithmetic sequences and series where you had a common difference. Today we're going to look at geometric sequences and next lesson series. And geometric sequences look like this, which again you will have seen at GCSE. But rather than having a common difference, they have a common ratio. In other words, there's a multiplicative factor. And so if we look going from 3 to 6 to 12, we can quite easily see that we are doubling. So we're multiplying by 2 each time. If we're going from 5 to 0.5 to 0.05, you can see it's getting 10 times smaller, but we always have a common ratio as a multiplicative factor. So it's times by 1/10, dividing by 10 or timesing by a tenth. And we can even have sequences that look like this, where the sign changes. And again, we've got smaller. It looks like it's being divided by 3, but what's the same as being divided by 3? It's being multiplied by a third. And because it's changing sign each time, it's being multiplied by -1/3. So, if we think about, again, we call A our first term in our sequence, and we use the letter R to denote the common ratio, so what we're being multiplied by each time. And again, we just use UN to be the nth term. Now, when I did my arithmetic sequences, if you remember, UN was A plus n minus 1 D. But we're not doing arithmetic, we're doing geometric. So let's have a look at this slightly easy one. We'll look at the first one. If my first term is A, my second term is A times R. My third term is A times R squared, because I'm multiplying by R. I'm going to multiply by R again, so I'm going to get A R cubed, multiplied by R, I'm going to get A R to the power 4. So the fifth term is A R to the power 4. The fourth term, is A R to the power 3. So for a geometric sequence, UN is A R to the power n minus 1. And that's what you have to remember. So let's have a look. I'm not going to go into some simple ones because it's fairly obvious how it works. But the fourth term is 10. And the fifth term is 20. Find the common ratio. So again, I've got U4 is 10. Now, in a geometric sequence, that means AR to the power 3 is 10. If I look at the other one, I'm told that the fifth term is 20. So U5 equals 20. So that means AR to the power 4 equals 20. Well, I've got 2 equations and 2 unknowns, so I've got a pair of simultaneous equations. Doesn't quite look like the usual simultaneous equations that we deal with, but that's what I've got, a pair of simultaneous equations. So I've got to solve them. And the way you could do it is you could say, well, I'll rearrange this first equation to say, well, A is 10 over R cubed, and I'm going to substitute that into there. So I'd have 10 over R cubed times R to the power 4 equals 20. These are going to cancel. So I'm just going to be left with 10R equals 20. So R equals 2. But there's a much better way of dealing with these sorts of equations. We would never do that. And what we do is we say we're going to take equation 1. And it doesn't matter which way around you do it, but usually you put the higher power on the top. So equation 1 divided by equation 2. So I say AR to the power 4 divided by AR to the power 3 is equal to 20 divided by 10. Because as you can see, you've got your first equation in the numerator, you've got the second equation in the denominator, and in that case the 2 A's cancel, and R to the power 4 divided by R to the power 3 just gives you R equals 2. So your common ratio is R. And then if we want to find the first term, well, we can use either of these. We know AR cubed equals 10. So a times 2 cubed is 10. A times 8 is 10. So guess what? A is 10 divided by 8, which is 1.125. No, it's not. It's 1.25 even. Okay. So, again, you can solve these things simultaneously. So let's have a look at a slightly different one. The 5th term is 24 and the 7th term is 2.16. So again, we say U5 equals 24. So that's AR to the power 4 equals 24. Because remember, the formula is AR to the power n minus 1. U7 is 2.16. So AR to the power 6 is 2.16. And again, if I do equation 1 divided by equation 2, AR to the power 6 divided by AR to the power 4 is 2.16 divided by 24. So you end up with R squared, because again the A's cancel, and you've got R to the power 6 divided by R to the power 4 equals 2.16 divided by 24, and you get 9 over 100. So my R is just going to be the square root of 9 over 100, which is plus or minus 3 over 10. Because remember, you can have a plus or a minus. So actually here, when it says find the 10th term, there's actually two possibilities. Most times with these sorts of questions, they'll tell you something to make it suggest it should be the positive or the negative. It might say all the terms in the sequence are positive, in which case R would be 3/10. But let's do them both. So I'm going to say if R equals 3/10, U10 is going to be, well, can I do U10 at the minute? No, the question hasn't asked me, but actually I need to find A first. So I'm going to do this on the side because I don't want to turn over the page. I'm going to say, well, I know A times 3/10 to the power 4 equals 24. So A is going to be 24 divided by 3/10 to the power 4. So A is going to be, I'm going to get my calculator, 24 over 0.3 to the power of 4. And you end up with a rather large number, 2,962.96. So then I can go back to working out what the 10th term is. It's going to be 2,962.96 multiplied by 0.3 to the power of 9. So times 0.3 to the power of 9, and we get an answer of, our U10 is just going to be 0.05832. And if I did want to say if R equals minus 3 over 10, I don't actually have to put it in. I just have to think, what happens to a negative number to the power of 9? Well, a negative number to the power of 9 is just going to be negative. So my U10 would just be minus 0.05832. Okay, so what other types of questions are they going to ask? Well, a bit like we did in the last couple of lessons, they might put a bit of algebra in the terms. And they might say the first three terms are 3x and x plus 6. So 3x and x plus 6. We know there is a common ratio. So we know that x is equal to 3 times r. Again, going from the second to the third term, there's a common ratio. So that means we know x plus 6 equals x times r. Now look, I've got two equations with two unknowns again. So again, it doesn't look like our traditional simultaneous equations, but that's exactly what we've got, a pair of simultaneous equations. And the way I tend to do these is I tend to write both as r equals. So if I go to the first one, I can say r equals x divided by 3, because I'm just going to divide by 3. If I go to the second one, I'm going to divide both sides by x, and I'm going to get r equals x plus 6 over x. Sorry, I switched them over, switched the order as well at the same time. But this is a common ratio, so r is the same in both cases. So I can say x over 3 must be the same as x plus 6 over x. And effectively, doesn't look like it at the minute, but this just forms a quadratic equation. Because if I get rid of the denominators by multiplying both sides by 3 and multiplying both sides by x, I end up with x squared is equal to 3 times x plus 6. So x squared is 3x plus 18. Really easy to do quadratic. X squared minus 3x minus 18 equals 0. So I'm going to have an x and a 6 and an x and a 3 equals 0. It's going to be minus and a plus. So either x equals 6 or x equals minus 3. Now it says all positive terms. So if x was minus 3, that wouldn't give a positive term, would it? So my x must be 6. So I can write down what my sequence is. It's going to be 3, 6, 12, because it's 3, x plus 6. Okay, because it wants me to find the 10th term. So if I look at this sequence, a equals 3, r equals 2, because we're doubling each time. So my 10th term is going to be ar to the power of 9. So my 10th term is going to be 3 times 2 to the power of 9, which is going to be 3 times 2 to the power of 9, 1536. Right. Can't remember if I've got one or two more left to go, but we'll see. So the third term of a geometric sequence is 12 and the fifth term is 36. Which term is equal to 2916? So start off with what we know. We know u3 is equal to 12, so that means ar squared is equal to 12. We know u5 is equal to 36, so that means ar to the power 4 is equal to 36. I'm going to do 1 divided by the other. So I'm going to do ar to the 4 divided by ar squared, which means I've got 36 over 12. So that means my r squared is equal to 3. So my r is plus or minus the square root of 3. And we can have surds occasionally. Okay. Now it says which term is equal to 2916. So I'm going to make an assumption first. So I'm going to say r is equal to root 3. Okay, and we'll see if it makes a difference. So r is equal to root 3. I don't know what a is yet, but I do know ar squared is equal to 12. So that means 3a is 12. So a is 4. Okay, so I want to know which term is equal to 2916. So in other words, ar to the power n equals 2916. So I know my a. 4 times root 3 to the power of n is equal to 2916. How am I going to solve this? Well, looking at it, I'm going to divide by 4 first. So I'm going to say 2916 divided by 4 is 729. So I want to know root 3 to the power of n equals 729. And thinking back to last year, this is where we have to then use our logarithms to solve this, okay? Because when the unknown is in the power, the way we solve it is to use logarithms. And we could think our root 3 is our base number, so something to the power n equals 729. I could say, well, that means n is log to the base of root 3 of 729. And that is a really easy and valid way to do it now, because our calculators can cope with this sort of thing. But occasionally, there's a better way. Sometimes you can't do that, or if this number's not particularly nice, if you've rounded or anything like that, it's not the best way of doing it. So you can do it that way. Or what you could decide to do is actually to take logs of both sides of the equation. And so I just use the natural log. So I'd have the natural log of root 3 to the power n equals the natural log of 729. I've just done the same thing to both sides of the equation. Thinking about our log laws, how do I get this power out of inside the argument of the log? Well, remembering our log rules, that means n times the natural log of root 3 is the natural log of 729. And so n is the natural log 729 divided by the natural log of root 3. And if we put that in our calculator, which is in a way it's a bit easier to do because you've got your natural log button. So 729 over the natural log of root 3, and you end up with n equals 12. Okay, but like I say, if you did want to use this first method and you did put that in your calculator, it would be absolutely fine. You can put the root 3 in the base and you can put the 729 in the argument and your calculator will do it. Okay, this second method is just a bit nicer really. So again, we can talk about when a term exceeds a number. So the first term of the geometric sequence is 20, so that's nice. This time they've told you that a is 20. And the fifth term is 80. So that means ar to the power 4 equals 80. Well, they told us what a was. So I've got 20 times r to the 4 equals 80. So r to the power 4 is 4. So r is the fourth root of 4. Now, if you put that in your calculator will come up with a decimal answer. But hopefully you can see that 4 is 2 squared. So r is root 2. Because root 2 times root 2 times root 2 times root 2 is 4. Okay. So my common ratio is 4. And we want to find the first term to exceed 1,000. So we want to know when un is bigger than 1,000. So that means I want to know when ar to the power n minus 1 is bigger than 1,000. I know what a is. A was 20 times root 2 to the n minus 1's got to be greater than 1,000. So that means root 2 to the n minus 1's got to be greater than 500. Just dividing both sides by 20. And now again, we take natural logarithms of both sides. So this is where I prefer to do taking the logarithms of both sides. And because I know that power is going to come out in front, then that means n minus 1 times the natural logarithm of root 2. I hope I haven't done that too quickly. In fact, I'll go back a step. Because really I'd have the natural logarithm of root 2 to the power of n minus 1. But we know with our log laws that the power can become a multiplier outside, but we put brackets around it because it's all of that is greater than the natural log of 500. So n minus 1 is greater than the natural log of 500 divided by the natural log of root 2. And so my n is going to be greater than all of that plus 1. And if we put that in our calculator, ln of 500 divided by ln of the square root of 2 equals 17.9, but then we've got to add the 1, and so it's got to be greater than 18.9. So the lowest value of n is 19. Okay, right, this is the last one now. So the second term of a geometric sequence is 80. So I'm just going to go straight to this. So we know ar to the power 1 equals 80, and the fifth term is 40.96. So ar to the power 4 is 40.96. Find the first term that is less than 1. Well, we're obviously going to have to work out what the first term is and what the common ratio is first. So I'm going to do 1 divided by the other. So that's 40.96 divided by 80. So that means my r cubed, because the a's cancel, one of the r's cancel. 40.96 divided by 80 is 64 over 125. which means my common ratio is the cube root of that, which is 4/5. Okay, let's use that in A times R equals 80. So my A is just going to be 80 divided by my common ratio. So A is 80 divided by that. No, it's not. It's 80 divided by that, which is 100. Okay, so I've got my common ratio and I've got my first term. And I want to know, when is UN less than 1? And this is an interesting one because as the terms went along, they're getting smaller. So there will be a point at which the answer becomes less than 1 because we're multiplying by 0.8 each time. So UN is AR to the power n minus 1, and we want to know when that is less than 1. So I've got when is 100 times 0.8 to the power n minus 1 less than 1. I'm going to divide by 100 first of all because I can't do my logarithms until I've got just something to the power of. So I've got 1 over 100. And now I can take my natural logarithm of both sides. And again, I'm going to do this in one jump rather than doing it separately. And I've got n minus 1 times the natural logarithm of 0.8 is less than the natural logarithm of 0.01. So this is where you have to be really careful, because it'd be really easy to say n minus 1 is less than the natural logarithm of 0.01 divided by the natural logarithm of 0.8. And that's wrong. There's a mistake there. And the mistake is only because we have an inequality. And I want you all now to put the natural logarithm of 0.8 into your calculators for me, please. And if you do that, you go natural logarithm 0.8, and you actually get that this is minus 0.223 ... It goes on for a while. Now, what is the rule when you divide by a negative number with an inequality? When you divide by a negative number or multiply by a negative number with an inequality, you have to change the direction of the inequality. Okay? So whenever you divide by a natural logarithm or any logarithm that is less than 1, you will have a negative number. And the reason for that is, if you remember what the graph of the natural logarithm or any logarithm looks like, it looks like that, where that is 1. So the natural logarithm or the logarithm of anything that's greater than 1 is always positive. But anything less than 1, change colour, is negative. So if you have the logarithm of 0.1, 0.7, 0.356, it's going to be a negative number, okay? So you need to then change the inequality sign around. So what we end up with is n is greater than, so if I put logarithm of 0.01 divided by the logarithm of 0.8, and then I'm going to add 1 to my answer, I get 21.6. So that means my n must have been 22. So it's the 22nd term. So the answer is the 22nd term is less than 1. Okay? So that's the answer to the question. Right, here's a few for you to have a go at. I'll just shrink my page. Press pause, do them, and then when you want to see the answers, press play again. Okay, so looking at the first one, the fourth term is 16. So we can say AR cubed is 16. The seventh term is 250. So AR to the power 6 is 250. You can work out that the common ratio is 2.5. And then if you put that into the first equation, you should have got A was 1.024. Right, second term. So again, you're told the third and the sixth term. Dividing those, you're going to get r cubed equals 8 over 27. So the common ratio is 2/3. Putting that into the first equation, you can get your first term was 243. Okay, and you want, again, the first term that is less than 1. So just like we did a couple of seconds ago, I want when ar to the power n minus 1 is less than 1. Put in the different values, and you're going to do, sorry, I've changed the way I do this sometimes. I don't solve it, so it's less than, but then because you're dividing by, it's greater than, so n has to be greater than 14.54, so n is 15. Now what you can always do is, if you're not sure about that, whether that should have changed direction, that sign, you can always put in, work out what u14 is and work out what u15 is. It only takes a few seconds, and you'll quickly see that u14 was still more than 1, whereas the 15th term was less than 1. Okay, so one of these where you're given the terms algebraically. So again, you know that x is 5 times r. You know that x plus 10 is x times r. Rearrange those both to be r equals 2. Make them the same, and you can show you have a quadratic equation, and you get x equals 10 and x equals minus 5. Now it says the terms have to be positive, so you can't have x equals minus 5, so you've got to have x equals 10. And looking at that, you know your common ratio is doubling. Your first term is 5, so your 10th term is going to be 2,560. Okay, so again, exactly the same as before. Okay, it says find the value of k, but again the terms are positive. If you've got k equals 0, they're not positive, because 0 is not a positive or negative number, so k must have been a half. And the last one, find the first term, which is larger than a million. So we want to know when ar to the n minus 1 is bigger than a million. So again, I'll change this. We want to find out when 3 to the n to the power of n minus 1 is bigger than 250,000. So take log. This was an interesting. I actually reverted back here and took log to the base 3 of 250,000, and you end up with n should be greater than 12.3. So it's the 13th term. But again, you can always do this thing of checking at the end. If you're not sure, do the 12th term, do the 13th term, and see which is the right answer. Okay, so have a go at the questions in the book, and I will see you next lesson.